Hi, welcome back. In this lecture, I'm going to continue talking about MPI-sided communication, and particularly, I'm going to look at the data movement and aggregation in MPI one-sided. MPI provides the ability to read, write, and atomically modify data in remotely accessible memory regions. We have MPI get, basically to read from an MPI windows. We have MPI put, to write to an MPI windows. And then we have a set of operations to basically do reduction and aggregation operation. So we have MPI accumulate, MPI get accumulate, MPI compare and swap, and MPI fetch and op. So the main operation to basically write to remote memory windows is called MPI put. So the MPI put moves data from an origin process to a target process. The description from origin and target data layout is provided by triplets. So for the origin data and process, we provide a pointer to the variable, the array that we want to send, how many, so the count, and then the data type of this array. We provide the target, and then we provide a triplet to describe the target process, and the data layout is going to move our data that we are putting to the remote process. So in this case, we don't provide a pointer to the windows, but we provide an offset. We provide a displacement from the beginning of the MPI windows where we want to write, right? And then again, we provide the counts and which data type that we are going to provide. And finally, we provide a handle to the MPI window. So complementary to MPI put, we have the MPI get operation that is basically a reading operation from the remote windows from the target windows to the origin. So we use MPI get to move data from target data to the origin. So we describe the origin again with a set of triplet. We provide the pointer to origin address, how many and which kind of data type. We provide the rank of the target data type, and then we provide a triplet of describing the target. Like in MPI put, we use a displacement from the beginning of the window. So we have MPI integer that is a displacement at the target windows. Let's look at operation for doing accumulation and aggregation. So we can use MPI accumulate. This corresponds to element-wise atomic update operation. It's basically similar to a put, but we do have an operation that we can use for reduction. So the way it's working is that it reduces origin and target data into a target buffer using an op argument. So we provided which kind of operation we are going to use for the reduction. So we can use only predefined operations, no user-defined operation like in MPI collective operation. It's okay to provide different data layouts between target and origins, and we see that we have a means to describe that. And we can also use operation MPI replace that is implement this basically operation. And this is basically element-wise atomic put. We also have the complementary to accumulate, that is get accumulate. So is very similar to accumulate, but is instead of putting, we are actually getting. This corresponds to element-wise atomic read modified write. It support several operations like MPI sum, MPI prod, MPI logical operation. It only supports predefined operation. The results are stored in target buffer. Original data store is a result in buff. Different data layouts between target and origin also okay, but the basic type elements must match. We can use get accumulate to do element-wise atomic get if we use MPI no operation. Also, we can use MPI get accumulate for doing element-wise atomic sweat swap with MPI replace as operation. Also, two other operations that we can use for aggregating and accumulating. They are the MPI fetch and op and MPI compare and swap. So the MPI fetch and op is a simpler version of MPI get. Accumulate is simplified because all the buffers share a single predefined data type, and also there is no count argument. So in this case, count always is just one element, right? So it's a simple interface that allows hardware optimization. So if there is a chance, MPI fetch and op is the way to go. Also, MPI one-sided provide atomic compare and swap. So it's called atomic swap. And basically, if the target value is equal to a compare value that we provide here as a terminal function. So let's talk briefly about ordering operation in MPI RMA. So there is no guaranteed orderings of put and get operation. Results of concurrent puts to the same location results in undefined results. Result of get concurrent put accumulate is undefined. So undefined also means that we can have garbage in both of the cases. Results of concurrent accumulate operation to the same location are defined according to the order in which they occur. So if you do atomic put with accumulate put with operation MPI replace, atomic get accumulate with operation equal to MPI no op. Accumulate operation from a given process are ordered by default. So the user can tell the MPI implementation that ordering is not required as the optimization hint. We can ask for only the needed orderings, for instance, read after write, WAR, RR, and write after write, right? So, but these are some optimization technique that it can be provided as a hint. RMA data, how is the RMA data access model and what does it mean? So this answers this question. When is the process allowed to read or write remotely accessed memory? And when is the data written by process X is available for process Y to be read? RMA synchronization models define these semantics. The three-synchronization model provided by MPI one-sided communication are first, fence, also called active target. Second, post-start complete wait, that is called generalized active target. And the third one is the passive target using lock and unlock mechanism. An important point when using operation on MPI windows is always that we need to define epochs. All the data access in MPI one-sided need to be within epochs. So we have access epochs that contain a set operation issues by an origin process. And then we have exposure epochs that enables remote processes to access or to update a target window. Epochs define orderings and completion semantics. Synchronization models provide mechanism for establishing epochs. For instance, starting, ending, and synchronization epochs. Let's look at the first synchronization, that is active target synchronization, that is called MPI fence. MPI fence. So this provides a collective synchronization model. It starts and then accesses and exposure epochs on all the processes in Windows. All the processes in a group of a win do an MPI win fence to open an epoch. So that means that everyone can make a put and get operation to the read-write data after we did we start our epochs with the fence. Also, everyone does an MPI fence to close the epoch at the end of our epoch where we did all the MPI put and get or accumulate. All the operation complete at the second fence of the synchronization. So we ensure that after this fence operation, all the communication is basically completed. The second way to open epochs is to use the generalized active target synchronization we have basically one function that is MPI. So we have 4 functions: MPI win post and start for the target, and MPI win complete and wait for the origin. So it's pretty much like MPI fence, but origin and target specify who they communicate to. So the target is dealing with exposure epochs, so that opens with the MPI win post and is closed by MPI with wait. At the origin, we have access epoch that is open with MPI win start and is closed by MPI win complete. All synchronization operation my blocks to enforce a post start ordering, and process can be both or origins and targets. So how we use active target synchronization? Well, active target RMA works well in many programs, including HPC typically application, for instance, Holo Exchange. So we can use MPI fence or generalized target to open and close the epoch. Also, all the operation of dense linear algebra work quite well with the target synchronization operation. So the question for you is how you might write dense matrix multiply using MPI get and put. In the next lecture, we'll look at how to do like passive synchronization. So a few more slides about synchronization, and then we will be done with the MPI one-sided communication, at least the theory. We might probably put some example how to use it. So that's it for the lecture, and talk to you soon.